Swayam Prabha. Digital India. Educated India.
Okay, welcome. So we have been discussing about the polymer size and structure in the previous few weeks, and we have discussed several models to look at the size of a polymer, and lately we discussed like how to characterize the polymer shape. So today we will start discussing about the structure, as we have suggested earlier that one other aspect is like how ordered or disordered the polymer system is, and we talk about polymers in general, not like a single chain, but it can be like a solution of polymers which can be concentrated containing many chains. So we will first take a detour, talk about order and disorder in general, then I will discuss experimentally how do we characterize order, and then I will come back to the theory of behind it, or how theoretically we can describe order, and then finally we will come back to the polymer physics and say like how does we apply those concepts in the polymer systems. So let us start with the description of order and disorder. What do we mean by order? So one way to start thinking about what we mean by order is to start thinking in terms of like how the molecules in the solid, a liquid and a gas are arranged. How does the distribution of molecules in a volume changes when I go from one phase or one state of matter to other state of matter. Okay. So if we know from the ideal gas theory, you know that there is no interaction between molecules. So in a gas, the arrangement of molecules are pretty random. Actually, in fact, in the ideal gas they can also overlap, because we assume the ideal gas to be a collection of point particles. So in that sense we do not really assign any kind of a size to the molecules. If I start thinking in a thermodynamic way, okay, of course at a molecular level one can question that what does the overlap mean and so on, but in a thermodynamic description it is often better to think of gases as like molecules which are like point particles and non-interacting. Okay. What it really means is if I start looking from any particular molecule in the gas phase and at any particular distance or distance vector from the molecule, it is equally likely to find a molecule at one distance and other distance. That means that the probability of finding a molecule is independent of distance, just because we have assumed the gases to be either non-interacting set of molecules or at most a weakly interacting set. That is what we do for the real gases. But what we mean is that the probability to find another molecule at a distance vector r is independent of the distance. Anywhere we go, we will have equal probability of finding a molecule. Then we say there is no order in the system. Okay. So we assume that gas is in a what is known as a disordered state. Okay. Another way to think of it is in terms of entropy. So, in the gas we assume entropy is very high, and entropy characterizes disorder. So, it means that we have a disordered collection of particle if I or molecules. If I start from one molecule, I can find another molecule here, here, anywhere in the volume with equal probability. As soon as we go to a liquid phase, this is no longer true, because as we discussed, a water molecule tend to form on an average 3 hydrogen bonds with its neighboring water molecules, although these 3 hydrogen bonding partners need not be permanent. So, water molecules can switch a hydrogen bonding partner for a different hydrogen bonding partner, but in general what we have said is, on an average a water molecule is participating in 3 hydrogen bonds. So, each of the oxygen is hydrogen bonded to one of the hydrogens of other water molecules, and the same is true for the hydrogens. And of course, the water molecules can switch partners, as we said. So, next water molecule can come here, and this hydrogen bond can go away and a new hydrogen bond can form. Okay. What it means at a slightly mesoscopic level is, if I look at water now, then very close to any particular molecule in the system there are 3 hydrogen bonds, okay, which means that at distances very close to water molecule, at small values of r, there is some sort of order. Why do I say it some order and not more order? Is the reason is that the water molecules which are nearby, they are connected by a hydrogen bond, and hydrogen bond itself is very weak. So, what it means is, of course, these 3 water molecules are connected to the water molecule in the middle, but then these guys can really wiggle around their positions as long as they remain close to the water molecule in question. That means that the positions of the partners are not fixed, but the distances have to be within a range such that it can form hydrogen bonds, and the one estimate is around 0.3 or 0.4 nanometer is a typical distance where hydrogen bonds form. So, it has to be within that particular distance, but there is no particular direction where the other water molecule will be, and that is why I would say it some order. It is unlike the gas molecule where there were no interactions between the molecules for the ideal gas. Even for the real gases, the interactions is very weak. In this case of liquid, it is still not so strong, it is still weak, but much stronger than what we have in the gas. Now, let us see what will happen in the case of a solid. So, this is a liquid. In the case of a solid, however, and if I start thinking in terms of say crystals, there we have a repeating pattern of molecules. Let us say, for example, if I think of a sodium chloride crystal, then you will have an arrangement in solid something of this sort, just because the the positive ions or cations attract the negative ions or anions, and so they tend to form a repeating pattern. In the bulk, what we see is a crystal structure, and what this amounts to is a repeating pattern of molecules. So, now unlike the gas, of course, there is much more order, the molecules are strongly interacting in this case, and of course, unlike the liquid as well, where the order was limited to very small range, that is, for the first near neighbor we have like hydrogen bond interactions, but they also can be pretty much anywhere as long as they remain close to the water molecule. Now, in this case, if I look at any particular molecule in a crystal, the other molecules cannot be just anywhere else, they have to be at specific discrete distances for a perfect crystal. That means that we can find a molecule say A apart, then 2A apart, then 3A apart, and this is an example of a cubic crystal. If we have a different crystal, we will have different arrangements. Similarly, along all the axes, along the diagonals also we can apply some geometry and see that the distance of the molecules are fixed. They can be either the unit cell length or some geometric factor multiplied by the unit cell length. Okay. So, in this case, both for small and large R, we have order. So, what I will call henceforth is in the liquid the order is somewhat short ranged, and in here the order is long ranged, and this gives us a way to look at the order and disorder in a material. Okay. So, again, if I go from a gas to solid, the order increases, and if I go from gas to solid, the entropy decreases, and this makes perfect sense because entropy is a measure of disorder. Okay. So, when we are doing the polymer chains, we defined the disorder in a slightly different way. We said that the number of possible conformations of a polymer chain are large. That means that polymers have high entropy. So, that is perfectly in line with what we are discussing here, because the molecules in the gas can pretty much be anywhere. So, there are many system conformations corresponding to a given density and temperature. Similarly, for the liquid there are many possible conformations, but lesser than what we have for the gas, and in solid we have even lesser number of conformations, because the molecules must form some kind of a repeating pattern and they cannot occupy any position in the space. They have to be at certain discrete distances from the neighboring molecules, and this extends to the second neighboring cell, third neighboring cell, and so on. So, that is why we call a long range order. Okay. So, we can say few things about the order and disorders. I will make some statements and I will give some physical justification for that, and then once we apply these ideas to polymers, these concepts can make more sense eventually when we discuss that. So, the first statement is the order to disorder transition occur with an increase in temperature. In fact, the order to disorder transition is also known in physics as phase transition. What essentially we mean is, if I think of water, if I go to very small temperatures, what we have is ice, and ice is of course rather ordered. If I raise temperature, eventually it becomes liquid water, which has lesser order, but is still somewhat ordered compared to a gas. And then if I further raise temperature, I get water vapor, that is almost no order. Okay, so not only in the case of this distinct phase transition from a solid to a liquid to a gas, as in the case shown here, it can also happen if I look within a phase. That means, if I look at water at say 20 degrees Celsius compared to water at 60 degrees Celsius compared to water at 80 degrees Celsius, they are all liquids, but if I look into it, the order is decreasing as we raise temperature. This is because the hydrogen bonding decreases. So, when I said on an average 3 hydrogen bond, that is typically at the room temperature, as we raise temperature it can become 2.5 to 2 and so on, and so eventually at very high temperatures we will have lesser number of hydrogen bond than compared to lower temperatures. So, although in a distinct manner we cannot see a macroscopic phase separation happening, but the order is changing with the temperature. Similarly, if I look at say a crystal at 0 Kelvin, that is minus 273 degrees Celsius, that is when we have the perfect crystal where the molecules are only present at discrete positions. If I raise temperature, let us say crystal at 0 degrees Celsius and crystal at 25 degrees Celsius, they will be less ordered. That means that we will have small wiggles around each of the positions of the molecules. The molecules will have certain vibration around their position, resulting in a decrease in the order. Okay. So, again order decreases and molecule vibrations increases. Okay. So, ultimately the game is happening because of the change in the entropy. As we raise temperature, entropy is increasing, and entropy always favors a disordered state. Okay. So, what this means is we can think of only the 0 Kelvin as the point where entropy does not have any effect. Then we have a perfect order going to the ideal crystal behavior or perfect crystal behavior I just described earlier. As soon as the temperatures become higher than 0 Kelvin, the molecular vibrations start to appear. At room temperature, they are quite significant, although it remains a crystal more ordered compared to a liquid counterpart, but still it is less ordered than compared to the 0 Kelvin crystal. Similarly, once it becomes water, there is first a big order to disorder transition. As soon as the crystal dissolves and become a liquid, there is a huge change in the order. It becomes highly disordered because there is a latent heat that is essentially released from there. And after that, again there are small changes in the order is decreasing as we raise temperature. Again we have a distinct jump at the boiling point, and that is when it becomes a vapor. So, we can think in terms of two ways of order disorder transition. One is the one that is discontinuous in some sense, or macroscopic, that is when the ice has become water or water becomes vapor, and other that is happening with a continuous change in temperature. Okay. So, the next statement I am going to make is somewhat related. That is order disorder transition occur because of a competition between enthalpy and entropy. So, if we look at the energy of the system, it has two parts. It has an enthalpic part and an entropic part. This is the part that is coming from all interactions within the system. Here G, by the way, is the Gibbs free energy. And this part is coming purely from entropy or disorder. Now, this explains, since temperature is in Kelvin here, that if I go to 0 Kelvin, we do not have any entropy term. As we go to higher and higher temperatures, we have a significant entropy term, and so the entropy becomes more and more dominant as we go towards more and more disordered state. Basically a restatement of what we have said earlier. Now, the third statement I am going to make is that the order can be measured using the average probability of finding another molecule at distance r from a molecule. This quantity is what we will refer to as a pair distribution function or a pair correlation function, and we refer to it as something called G of R. Okay. And this goes back to the idea we started with. So, for the case of a gas, we said that no matter where I go, I will find the same probability of finding another molecule from any given molecule at any distance. As we go to a liquid, we start to have some sort of an order. Every water molecule have some neighbors which are connected by hydrogen bonds, but that does not extend to long ranges. And in the case of a solid, we do have a longer range order. This extends to long distances. So, basically the way it turns out is, if I look at this G of R versus R, and I can look in terms of absolute value, at least for the case of for the gas, is a constant for an ideal gas. For ideal gas, it is not a constant, but it is still close to the ideal gas behavior. If I look at a liquid, again we can talk in terms of an absolute R value, because as I said, the neighboring water molecules can be at a particular distance, but they can be in any direction, because they can orient themselves differently while maintaining the same distance or a distance range that is required for a hydrogen bond. So, we get something of this particular sort. What this means is, at very short distances we do have interaction that give rise to some sort of a peak at small distances, but eventually it really dies off, because at long range we do not have any order. It is also important that we started from 0 here, or the origin here, and the reason is, in the case of an ideal gas, we do allow for the overlap of molecules. The molecules can overlap because they are assumed to be like point particles. We do not make that assumption for a liquid, okay, and for the reasons we will discuss eventually. For the liquid, these overlaps are penalized. They are assumed to have a certain size, and because of that we always start from 0. I will come back to this point as we go in the course. So, and then if I look at, this is for a liquid, and then if I look at a crystal, now we can no longer talk in terms of absolute values of R, because now there are discrete positions along directions where the molecules are present. So, let us say, for example, if I start from here, I find a molecule here, let us say this is my x and y, another here at distances a, but if I go along the diagonal, I will find the first molecule at root 2 a, where a is the unit length. The next molecule will come at a 2a distance along the x, 2a along the y, but 2 root 2a along the diagonal, and this, by the way, is a simple cubic crystal. The actual distances will change if I go for a different crystal symmetry, like a body centered cubic or a face centered cubic. Okay. But what this essentially amount to is there are only certain positions which are allowed, and everywhere else this is equal to 0, because we cannot find a molecule in between 0 to A, only we can find at A. Similarly, between A to root 2A, in the case of a simple cubic, we cannot find any molecule, we only find at root 2A. Similarly, for root 2A to 2A and so on. We can extend this idea, but there are only particular positions where we do see a molecule. So, this is for a crystal, actually a perfect crystal to be precise, at 0 Kelvin. Now, there can be departures from this behavior. So, if I for example think of crystals at room temperature, they will not be quite like this. What they can be is, for example, so this still has peaks, but now the peaks are somewhat broader, that allows for vibrations around those positions. Similarly, for the case of a liquid, this is one of the ideal cases we can think of, but for a real liquid it can be having more than one peak. Similarly, for the ideal gas, this is the behavior. For real gases, it can show some behavior that is not quite a straight line, but close to a gas. Okay. So, this also has some analogy in terms of states of matter, that is, we do not always have something that is an ideal gas or a liquid, we can have things in between that shows certain characteristics of the liquid and certain characteristics of the gas. Similarly, we can have things between liquid and solid that shows some certain characteristics of the liquid and certain of the solid. And so, with this G of R, we can essentially talk not only in terms of whether the molecule or the system of molecules is forming a solid, liquid or gas, but we can talk in terms of how much solid like the molecule is, how much liquid like the molecule is, and how much gas like the molecule is. For example, if we have a polymer gel that we will discuss in the class, the polymer gel is between a liquid and a solid. We can talk about how much liquid it is and how much solid it is, and what happens if I change, for example, certain parameter, let us say the amount of solvent contained in there, and how the liquid like part and a solid like part will change as a function of the quantity I am changing. Okay. So, we will come back to this. The basic idea is this particular type of measure will help us characterize the actual amount of order present in the material and characterize whether it is akin to a gas, liquid or solid, and if not, then if it is in between those two, then how much of liquid it is, how much of solid it is, or how much of gas it is, how much of liquid it is, where exactly it fall in the spectrum of the phases that we can obtain. I will make a couple of more statements and then we close. So, the next statement I am going to make is the order disorder transition can be macroscopically observed. What it means is by naked eye in informal language in certain cases. Let us say if I am going from ice to water, I can see the melting happening. Similarly, water to water vapor, I can see the boiling happening in a macroscopic setting, we can see by the naked eye. However, in other cases where I cannot see using naked eye, then I can see maybe using a optical microscope. So, then we say it is a microscopic observation. And then, as we are going to discuss, is in some cases even the microscope will not give you a very high resolution, the normal optical microscope, and then we can use the idea of scattering that we will discuss in the next class. So, the order disorder transition can be observed at submicroscopic scale using scattering. So, in the earlier case it was an optical microscope, that is very similar to optical microscope is like the camera you have. If it had a very high zoom, that is the principle that is at play in a microscope. Essentially, a very high zoom will give you a microscope. On the other hand, scattering is based on somewhat different ideas that we will discuss in the next class. So, and finally, related to the statement 5, I will put in here is the Fourier transform of G of R is related to something known as structure factor, which I will call something like G of Q, and I will discuss that in the next class, found using scattering. Okay. So, this is all we had regarding the order disorder transition. We have made certain statements regarding this transition. Before that, we have discussed what order and disorder means. So, in the next class, I will start talking about scattering in more detail and tell you how exactly we see that within an experimental setting. Thank you.